Welcome to What is Up with Quadratic Sequences. I'm your host, George Arrington, and in this third and final part of this series, we're going to look at what's called the automaton approach. Let's see what that's all about. So again, remember that a quadratic sequence is a sequence of numbers that's generated by this formula. The value, or the S sub n, which is the element in the sequence, is equal to an squared plus bn plus c. And n is equal to 1, 2, 3, 4, 5, and so on, as far as you want to go out. And in the previous videos, I gave you a sample problem, 5, 11, 23, 41, 65. And given this sequence, what our goal was in each of the problems was to figure out what A, B, and C were, and then given that, we would be able to find any value, any element in the sequence by just plugging in a value for n. So in video 1, we saw what was called a recipe approach. Basically, this was a series of steps that we would use to figure out a particular sequence, and there was really not a lot of rationale behind each of the steps. It was just like a recipe on making a cake. You know, you pour in some milk, you stir in an egg, some flour, etc., and then you get the cake. Well, likewise, you do a series of steps that you were just following and got the answer. Video 2, on the other hand, we used algebra to justify why this works. We started with the equation above. We plugged in values for n, and we got a series of 3 equations that we could use to solve for any of the values in the sequence. So now in this in this video, we're going to approach it with what's called the automaton approach. So let's see what that's all about. But first, a simple math problem. Okay, are you ready for a simple math problem? Okay, here goes. All right, what do you say? Well, if you said that the answer is x equals 4, I would say, well, that is an answer. Yes, that is an answer. However, that's not the answer to my question. What the general answer would have been is, well, what is the question? And the question is, what are the detailed steps that are required to solve for the unknown in this type of problem? Okay, so given any kind of problem in this particular format, what are the detailed steps required to solve for it? Okay, so the question was a little bit different. So that's the question, and so we're going to look at a series of 4 steps necessary to solve this equation, and then we're going to use those same 4 steps to solve the larger problem. Oh, by the way, in using those 4 steps, we're going to be restricted to a couple of things. Well, first of all, we're going to use real numbers, so we're going to use the whole real number system. But you can only use addition and multiplication, I should say, and or multiplication, to solve for each of the problems. So that's all you have. So if you looked at this problem and you said, well, I solved it by dividing by 3. Well, in our upcoming problem, you can't use division. You can only use addition and multiplication. So we'll have to figure a way around being not able to use division. So, what are the steps to solve this? Well, the first step is to find the multiplicative inverse of the x coefficient. Okay, that's a lot of complicated words. What does that mean? Well, what it means is to say take the number that is the number when we multiply it by that coefficient will give us 1. And so we say, well, in this case, that would be 3 to the negative 1, or 1/3. The next step is to multiply both sides of the equation by the multiplicative inverse. So we would get 1/3 times 3x on the left side, and 1/3 times 12 on the right side. Now, you may say to yourself, oh, but isn't that the same as dividing by 3? Well, effectively it is, but in the cases that we're going to look at here in a couple of minutes, we'll see that we can't really easily use division. So we have to use 1/3. And in fact, this is in keeping with our earlier restrictions, because 1/3 is a real number. So we can use 1/3. We just can't divide by 3. Okay. And then the next step, the third step, is to actually do the multiplications. Well, 1/3 times 3 is 1. And 1/3 times 12 is 4. And the nice thing about 1 is that 1 is what's called the multiplicative identity, so that anything you multiply by a multiplicative identity will give you that same thing back. So here in this case, and as we'll see in step 4, we simplify it by saying 1 times x is equal to x, and we've already figured out 4. So we simply say, we report the answers as x equals 4. So now let's look at our quadratic sequence in our quadratic sequence problem in a little bit different light. Now, we've already seen that any quadratic sequence problem can be written like this, where we have on the left side we have these 3 equations: a plus b plus c equals some value, equals the first value in the sequence. In this case, 5 was our first one. And then 4a plus 2b plus c is equal to 11 in this case. And 9a plus 3b plus c is equal to 23. The equation, the terms on the left side of the equal signs will always be in that form. They'll always be those numbers. The numbers that will change will be on the right side. So those were the first 3 elements of our sequence. So what I want to do is look at this in a slightly different way. Instead of trying to solve it in ways you may have already used in algebra, we're going to say, look at this and say, we have on the left side, we have some numbers, those numbers that are in front of the variables, and we call those things coefficients. So what we have here is we have some coefficients, and they're arranged in a certain pattern. We'll look at that pattern here in a second. Now, those coefficients are multiplied by our unknowns, and the unknowns are in a certain pattern, and we'll deal with that in a minute. And that whole mess on the left side is set equal to some, what I'm going to call, values. So we have coefficients times unknowns equal values. Now, the coefficients are arranged in a certain pattern. And the way I'm going to write it down is in a box. I'm going to put all of those coefficients into a box so that it looks like this. Okay, so if you notice the coefficients, the first ones are 1, 1, and 1 in the first line, 1, 1, and 1. The second line are 4, 2, and 1, and in the third line 9, 3, and 1. Okay, it's just a box. Okay, it has you notice it has 3 different lines, and we'll talk about that in a minute too. Now we're going to multiply that by some variables. Well, we really only have 3 variables here, so I'm going to just put those in a vertical box like this, and we're just going to say that's those things are multiplied by A, B, and C. Now, how we multiply those, don't worry about that quite yet. I'll be doing most of that for you, so don't worry about that. And then we set that multiplication equal to the values on the right-hand side. And since they're kind of in a vertical box also, I'll just put them in another vertical box like that. So there's our new way of writing this equation. Now, if this looks scary to you, don't worry. I'm going to do all of the hard work, and you'll see how well we can get the answers from this. Okay. Now, also what I want you to notice is that this arrangement of coefficients times unknowns equals values has exactly the same shape as this. This is the problem we did earlier, 3x equals 12. So we have, in 3x equals 12, we've got some coefficients times a variable and equals a value. Okay, 3x equals 12. Surprisingly, the way we solve the problem with the numbers in the boxes has the same pattern as the way we solved 3x equals 12. Let's see that. Okay, first off, let's just give some names to all of this. The box that has 1, 1, 1, 4, 2, 1, and 9, 3, 1 in a box is given a particular name. It's given the name a matrix, and notice that it has 3 rows, and if you look at it vertically, it also has 3 columns. So this is a 3 by 3 matrix. And when a matrix has the same number of rows as it does columns, we call that a square matrix. And I'll just let you know that there are matrices that are not square. There are some that are longer than they are wide and wider than they are long, and so forth. So but this one has the same number of rows and the same number of columns. We call it this 3 by 3 matrix. We call it a square matrix. Now the next box is a vertical box that has A, B, and C in it, and it is also a matrix. In this case, it is a 3 by 1 matrix. It has 3 rows, 1 column, and anything that has a 1 of either a row or a column is called a vector. So in this case, we'll say that this vector, the square matrix, is multiplied by a vector. Okay, and it is set equal to, as you might guess, another vector. In this case, it's the values that are on the right side of the equation. Okay, and since these are written in a vertical format, they're both 3 by 1 vectors, or 3 by 1 matrices. These vectors are called column vectors. So we say we have a square matrix times a column vector is giving us another column vector. In other times that we use matrices, you might have a 1 by 3, which would be a row vector. But we're not using that in this problem, so we won't get into that. Now, one thing about what you're seeing here is this is all part of a branch of mathematics called linear algebra, or sometimes called matrix math, matrix algebra. The purpose in this video is not to teach a course in linear algebra. That could, that could be a whole course in and of itself, and it is a course. So we won't get into that, but I just wanted you to know that. So let's now solve for the unknowns. So again, you may be saying, I don't know how to do this kind of mathematics. That's okay. I'm going to do all of the heavy lifting for you. I just want you to appreciate what you see. All right. So let's start off by considering the strategy that we used with 3x equals 12. If you recall, the first thing we did was we found the multiplicative inverse of the coefficient. In this case, we have a square matrix, and so we have to figure out what is the multiplicative inverse of this matrix. Well, with matrix math, you don't just say 1 over the matrix. You have to do some specific things. And again, I'm not going to ask you to do that. I will do it for you. The only thing I would caution you about is when you see this thing, it's probably going to alarm you. It looks very scary. Here, let me show it to you. Be careful here. This is a very shocking image. Look at that. Isn't that terrible? You have numbers. First of all, you might notice that you do have a 3 by 3 matrix here, but it's got like decimal numbers in it, and it's got negatives, and it's scary looking. But again, don't worry about that. It's just a thing, and we're going to use that thing in the same way that we did the earlier 3x equals 12 problem. Now, what was it that we did with that multiplicative inverse? Well, remember what we did was we multiplied both sides of the equation by the multiplicative inverse, but this time we're going to do that for using the multiplicative inverse of the square matrix. And this is going to, if the last one looks scary, this one's going to look 3 times as scary. And you notice here that this is a real mess. And if you were just to see that in a textbook, you would find that very difficult to deal with. But realize that all it is that thing that we talked about in the previous slide times the thing above. So we have the multiplicative inverse times that original square matrix times that column vector equals that multiplicative inverse thing times the column vector that had the values in it. Okay, that's all it is. Okay, so now it comes down to doing the multiplications. Well, how do you, I don't know how to, you might say, I don't know how to do the multiplication here. Again, I'm going to do it for you, so don't worry. So we have 2 multiplications we've got to do. We've got to do the multiplicative inverse times that square matrix, and the multiplicative inverse times the column vector with the values in it. Okay, are you ready? Here we go. Well, that's not too bad. Okay, so now the matrix in front of A, B, and C has changed a little bit. It's not quite as scary. In fact, it looks pretty orderly. All it has is 1s and 0s in it, and the 1s are down the middle. That's not too terrible. And then, oh, wait a minute, look over on the right-hand side. We've got just one column vector there, and somehow those numbers remind me of something. They look a little bit familiar. Let's see what that's all about. Okay. First off, remember that the fourth step in solving was to simplify and report the answer. Now, first off, this new somewhat friendly-looking square matrix has a name. It's called the identity matrix. Just like when you said 1/3 times 3 and you got 1, when you take the multiplicative inverse of a matrix and multiply it by the matrix, you get what's called the identity matrix. And if you recall what the nice thing about an identity, a multiplicative identity is that if you multiply it by something, you get that something. So indeed, if you have the identity matrix times that column vector ABC, you will indeed get ABC. Pretty simple. So there's our simplification. And so now we report the answers. Well, what I want you to do is I want you to look at something with what I call common sense. And it says here a column vector ABC vertically is equal to another column vector vertically 3, -3, 5. What makes sense to you when looking at this? If A, then B, then C is equal to 3, then -3, then 5, doesn't it make sense that A is equal to 3 and B is equal to -3 and that C is equal to 5? Okay, and that C is equal to 5. Well, yes, and that is indeed what it is. And if you recall, those were the coefficients for A, B, and C that we found way back in the previous video. That was the answer. Once we have those, we can then plug those into the formula for a quadratic sequence and get any value we want, like for instance the 12th item in the sequence. Okay, so there they are, and by using this matrix math that you don't necessarily know how to do, we were able to very quickly get the answers. Okay, so you're asking, what's up with this robot business? Well, a robot, another word for a robot, is an automaton. And an automaton can do a lot of things for us. First off, it can do a lot of hard work for us. It can do things that we have to do over and over and over again, a drudgery kind of thing. It can also do things that are difficult to do for us, heavy lifting, if you will. And it can also do things that are very require accuracy in performing the tasks. So we have robots that just put labels on cans over and over again, thousands of times a day. Or we have things that robots that lift up heavy parts and put automobile chassis together. So we have things that do heavy lifting. And then we have robots that go in and do surgery on people that requires very minute things that a doctor's hands might not be able to do with great precision. So we have robots that do all of those sorts of things. So the robot icon there is kind of a way to keep up the curiosity in the video. And what we're going to do is we're going to take a robot, a form of a I won't really call it a robot. It's a device, a method, a tool to solve these problems over and over and over again. And what that thing is is a spreadsheet. In this case, I'm using Google Sheets, but you could use your own favorite spreadsheet like Excel or anything else that you use. There will be one caveat for that we'll see here in a moment. Now, on this spreadsheet, if you look at it, I just want to kind of give you a tour of this. The first thing we'll see is that right there are the coefficients of the three equations. In other words, that's that matrix that we saw earlier. And the way that I put this into the spreadsheet is I simply typed it in as you see there, starting in cell A1. I typed 1, then moved over a cell to the right, put in 1, then put in a 1, then the 4, 2, 1, and the 9, 3, 1 in the format that you see there. Next, I put in, and I simply just typed in 5, 11, and 23, like that. But in this range of cells, I put in a formula that we're going to see that calculated the inverse of the matrix above it. And one of the caveats that you have to have for this particular spreadsheet you're using is it has to be able to do matrix mathematics. And Google Sheets has that, Microsoft Excel has that. Most of the modern ones will have a form of doing matrix math, and we'll see how to do that in detail. And then this is also calculated using a matrix function, and we'll see how that's done. Then once we have the A, B, and C there, the 3, -3, and 5, we can then generate a table of values for n and S sub n. So we generate a table there. We'll see how that's done, and then that's nice to be able to look at. And by the way, you notice that if you remember the original sequence, 5, 11, 23, 41, 65, those were the first 5 values of the sequence. And it keeps going after that. And then last on this spreadsheet is I wrote a little calculator. And by the way, I put labels N and SN above this. I didn't do that on the previous part of the sheet. You could if you wanted to, but for this one I put the labels here. And so N, that 12 there, is just a blank cell. You could put any number in there, and then the cell to the right of that, it says 401. That's actually calculated using the 12 and the 3, -3, and 5. So so if you wanted to type in, the 40th or the 100th of the 100th of the sequence, you could do that just by typing it in, and that would give you the answer. Now one other thing about this spreadsheet that's very cool is that here you could then go back. Let's say that you had a different problem and you wanted to find out the parameters for a different quadratic sequence. Well, all you have to do is simply type in 3 new values here for the first, second, and third elements in the sequence, and then everything in the spreadsheet will change, and you'll be able to figure out any problem with that. So that's how that looks. So let's get into the specifics of how to create this spreadsheet for yourself. So I'm zooming in here to look at one part of the spreadsheet. So the first part there, you see the 1, 1, 1, 4, 2, 1, and 9, 3, 1. You type that in just as you see there. And then the 5, 11, 23, you would type that in based upon your particular quadratic sequence problem. But this part requires a mathematical matrix function to solve this. The way you do this is you take your mouse and you select the area that you see there that's bounded in the dotted in the dotted lines. Now that has to be, and for this example, let's pretend for just a moment that there was nothing in rows 5, 6, and 7. So there, let's assume that those are blank for just a moment. So you select that area, and that area has to be exactly the same shape as the matrix above it, or the matrix that you're finding the inverse of. So you select that shape, and then while your cursor, or your focus, I should say, is on cell A5, you type in this equation. Equal minverse, and what that means is matrix inverse, and open parenthesis A1 colon C3. So what that says is take the matrix inverse of cells A1 through C3, which if you look above, those are the cells that contain the original matrix. Close the parenthesis, and on Google Sheets, if you press equals, I'm sorry, if you push, not equals, if you push enter, you will get the values that you see there. And that works essentially the same way with the latest version of Microsoft Excel 365. But if you're using an earlier version of Microsoft Excel and you push enter, you'll only get the 0.5 there in cell A5. You won't get the other values. So if you're using an older version of Microsoft Excel, you have to use what's called Control-Shift-Enter to populate the rest of the box there. So check your manual on that, but that's how that's done. And again, I'm using Google Sheets for this one, which is a spreadsheet that you can get off of the web. Okay, next we're going to find out the A, B, and C values, the 3, -3, and 5. And to do that, remember what we had to do in the problem is we had to multiply that multiplicative inverse matrix, which is seen in A5 through C7. We had to multiply that by the 5, 11, and 23. So a matrix multiplication is done in the following way. You select a blank area, and again, let's pretend like this is a blank area on your spreadsheet. You select a blank area that is the same shape as the column vector above it. So in the same shape as the 5, 11, 23, we select a shape with our mouse, and we leave the focus on, in this case, E5. In that cell, we type the following formula. Equals mmult, which means matrix multiplication, open parenthesis, A5 colon C7. What that means is the rectangular or the square matrix here, A5 through C7. That's what the colon means. It means through. And then comma means that there's another thing that we have to input here, and that is E1 colon E3, or E1 through E3. And that's the column vector that represents the results, 5, 11, and 23. And once again, on Google Sheets, if you hit enter, you'll get those three values. And on Excel, use Control-Shift-Enter. All right, so now we have the A, B, and C values. We can then generate a table if we'd like. So in generating a table like this, the way that I would do this, the quick method, is as follows. First type the 1 and the 2, and then select 1 and 2. So let me say that again. Type in G1 and G2, type 1 and 2. The number values, the row values are cut off on this picture, but you type in G1 and G2, type 1 and then 2, and then select them. And when you do so, you'll see a little square in the lower right corner of that selection. And what you do is you take that little square and treat it like a handle. When you hover your mouse over that, it will turn into a cross. You grab hold of that by clicking the left mouse button and dragging down, and it will produce and when you release it, it will produce a table based upon the pattern that you see, or that it sees in the first two cells. So it notices that it's 1 and then 2, and so the next one will be 3 and 4 and 5 and 6. So it'll be an arithmetic sequence that differs by 1 each time. So that's how you can quickly generate those. I mean, you could, if you wanted to, type 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but this is quicker. Okay, now in the H column there, what you do is you select that cell, and again we'll pretend that that's empty at this point, and you type in this function. Now this is kind of complicated, so let me go over this. Essentially what you're typing in is an squared plus bn plus c. So a is located in E5. If you notice there, if you go over to E and count down 5, that's the a value. Okay, now for reasons that you'll understand in a moment, or you might already understand, is that I'm using dollar signs in front. What that means is this is going to be an absolute reference. It's not going to be what's called a relative reference. It's going to be an absolute reference when we type it in. So it's $E$5 times, now G1 is the cell that contains the n value for this particular cell, and then we use the up arrow and 2 to indicate squared. So this is A1 squared plus, now we go $E$6, which is the B value, times G1. So remember, that's B times N. And then finally, we type in plus the C value, which is at E7. And again, we use the absolute reference, $E$7. All right. Once you do that, you'll get the value of 5 after you push enter. Likewise, from the generating the 1 through 10 sequence there, you'll have a little handle below to the lower right of this cell, and if you grab hold of that and drag it down, you will get the values for each of those values in the sequence, and they will be relative to the number on the left of each one of those, the n values. What will not change are the A, B, and C values. So those will remain at E5 and E6 and E7. And that's why we had to use the dollar signs. So finally, on this particular spreadsheet, we're going to type in the little calculator that I had. So again, remember, the question said, given this particular sequence, what's the 12th number in the sequence? Well, if you have this set up like this, you can say, all right, I just type in 12 there in cell J2, and it would automatically type 401 there cell K2. So how do you do this? Well, first off, you type in N in J1 and SN in K1. Those are just labels, so we can look at that. And I right justified those so that they appear to the right. Normally, when you type in labels, they will left justify the labels. So these are right justified. In cell J2, I typed in 12. There's no magic there. And then in cell K2, I typed in the following. And this is exactly the same format as you saw in column H. Now, one shortcut here is that you can go over to H1 and do a copy. In Windows, it would be Control-C, and then go over to cell K2 and do a paste, which in Windows would be a Control-V, and it would do all of that for you because it's now relative to the cell to its left. And again, since we used absolute references on E5, E6, and E7, those would not change. So that's a kind of a shortcut there. So there's our spreadsheet, and here's another look at it. That's the whole thing, and you can then use that to solve this problem. And then in the if you're doing homework, you would then take this and plug in, if you had for the next problem that may be different, you would plug in different values at E1, E2, and E3, and then you could get the answers very quickly. So what's the assessment of all of this? Well, first off, matrix math might be a little bit confusing to you, but again, remember I did all of the heavy lifting in terms of the actual doing the math, and quite frankly, you had a robot do it for you. Well, typing the spreadsheet takes time. Okay, yeah. And could you do this on a test? Probably not. You'd probably have to have some other method to do this. Set it up on your calculator. But for homework, it's not a bad way to go. And the nice thing is that if you have this, any quadratic sequence can be easily tackled with this method. So once you have the spreadsheet set up, any quadratic sequence that you have, you just plug in the first three values and there's your answers pretty much. But you might ask, what about quadratic? This is only for quadratic sequence. What about for cubic sequences or quartic or quintic sequences? Is this stuff extensible? Given the following cubic sequence, what is the 12th number in the sequence? Hint, it won't take you a leap year to finish this. So here's another hint. If you have a cubic sequence, you would simply start with this and then do all of the steps that you've seen in this preceding video. Here it is for quartic, for fourth power sequences, for fifth power sequences, and so forth. So you notice that now you have, for cubic, you have one more variable. You have A, B, C, and D. So you would need 4 equations. For fifth power, excuse me, for fourth power, for quartic sequences, you have 5 variables. You need 5 equations. For fifth power, you need you've got 6 variables. You need 6 equations. But again, once you set up the spreadsheet for it, it's the same kind of effort. And as a matter of fact, you can pretty much set up a 6th power or 7th power or even a 10th power set of equations in about the same time it takes to do 3. A little bit longer because you have to actually type stuff, but it can be done very easily. So anyway, I hope you enjoyed this series of videos. If you do, give me a like there and be sure to share it with your friends. And I'll see you next time.